Yes, good morning, everybody. Can you listen to me? Please raise your hand. Today again will be a very, very important day, which I will review. In 2 minutes, I am going to start. But meanwhile, everyone try to do this problem. Everyone try to do this problem. Tomorrow's class, I think it will be there. No, no, no. The schedule doesn't mean that you will not get. Almas Ali, raise your hand. Yeah, tomorrow, if suppose evening class is there for more hours, I will give only from 7 to 11 like that. Seshu will decide. Actually, Seshu was telling that some other subject is going in the evening. It's not for you. Yes or no? Raise your hand. So some other subject is going. So if that is there, he requested me to only continue from 7 to 11. Like that, we will plan, sir. Otherwise, I will take up to 7 to 1. Okay, na? Don't worry. But your time will be utilized. Okay. If evening class is not there, I will take from 7 to 1 or 1:30. If evening class is there, I will take only from 7 to 11. Like that. Okay, na? Please, we will not waste your time. Okay. Chalo, everybody. See, I told na, sir, even my case, because I'm having this video recording and also another batch. That is the reason I could give you this much time, sir. But effectively, I'm going. So please understand, I'm going effectively. Okay, na? No, no, it will not be over today. Who told it will be over? Yeah, I'm going to extend. Evening class subject will be over today. Then I will take tomorrow from 7 to 1. Don't worry. Okay, then I will take. Don't worry. That we will take care, sir. Only be ready with the schedule. Whatever message you get or whatever you get tomorrow, be prepared for it. Okay, na? Okay. So please, that I will talk with schedule manager. Okay, na? Chalo. Now, sir, everybody. See, quick review what happened in the last class. Quick review. Okay, na? See, last class we started the main thing called AC steady state. Steady state AC circuit analysis or sinusoidal circuit analysis. I call this steady state AC circuit analysis as Sinusoidal circuit analysis. Please understand. Yes, sinusoidal circuit analysis. Okay. The question come, why number one AC waveform is sinusoid? Sinusoid means it can be either sine wave or cosine wave, anything you can take. But why number one AC waveform is sinusoid? Though there are so many AC waveforms in the world, but why this is the best? The best simple answer is regarding the economics and performance. So the answer comes from the reason of economics and performance. The best wave in electrical power engineering, yes, the best wave in electrical power engineering, where our entire generation, transmission, distribution, and utilization of electrical energy, where all our major components such as alternator, transformer, transmission lines, and induction motors give highest efficiency and power factor is only with sinusoidal waveform. Okay, give highest efficiency and power factor is only with sinusoidal waveform. Okay, alternator, transformer, this all give highest. But if we excite, yes, but if we excite our major components with other than this signal, suppose if you give such waveforms to our induction metal, they may work. But what are the problems? High torque ripple, harmonics, electromagnetic interference, losses, low power factor, and low efficiency. Okay, na? This is efficiency I'm talking. Then another important reason is the only waveform you give to any linear RLC circuit as input, you'll also get it as output is which waveform? Sinusoid. Only magnitude and phase may change. Then we represent sinusoid in radian mode, okay, degree mode, and time mode. All are important. In India, one time period is 20 milliseconds per 50 hertz, and omega is 314 radians per second. So one time period is either 2 pi radians or 360 degrees or 20 milliseconds in all domains. Then what is the meaning of leading lagging? If you see any plus phase shift in any signal, +5, that means that is signal is coming early by this much phase shift. Okay, leading means coming early. Okay, -5 means lagging, coming late. -5 means lagging, coming late. Okay, then India, frequency 50 hertz. Yes, for frequency 50 hertz. Phase shift 60 degrees means corresponds to 3.33 milliseconds. Okay, phase shift 60 degrees means corresponds to 3.33 milliseconds. Okay, na? Yes, phase shift, let me come there. In India, yes, phase shift 50 degrees means, like example, 3.33 milliseconds. Suppose I say phase shift is 90 degrees, then 360 is 20, okay, and 90 becomes how much? 5 milliseconds. Like that, there is a meaning. Okay, 30 degrees means 1.66 milliseconds. Okay, 45 degrees means 2.5 milliseconds, like that. So, though we are all talking phase shift in degrees, but actually it is time only. Okay, then ideal DC versus ideal AC. Ideal DC is very simple. It is like simple constant value. Inductor is short, capacitor is open, and there is no leading lagging. And everywhere it is constant value. So instantaneous value itself is the steady state value. But here in AC, voltage keeps on varying, magnitude and phase, leading lagging, frequency can change, etc. So that is not easy. Then how to do it simplified, how to make it mathematically more simple by introducing a phasor concept. Okay, so we can simplify our AC circuit analysis with sinusoidal excitation by using phasor concept or phasor notation. What is phasor? Okay, phasor looks like a vector at an instant, but it continuously rotates at system frequency of omega. Yes, omega in the positive anti-clockwise direction. Okay, na? Like imagine in India, in our houses, factories, everywhere, all our voltage, current, flux, power waveforms are rotating anti-clockwise with omega 2 pi f, that is 100 pi radians per second, like that. Fast they are rotating. Now, if you project the phasor looking from here, we get sinusoid. So phasor projection gives sinusoid. Like in 1 second, okay, 100 pi radians, it will give 50 cycles. That's the meaning. 50 cycles it will give. 50 cycles it will give. Okay, in 1 second, 50 cycles it is. That is the speed of this phasor. So in AC, I will take one point in the waveform as one instantaneous value, and that represented as a position of phasor like R angle theta. That is why in this chapter, voltage we take 100 angle 30 volts, 100 angle 0. See, 100 angle 0 is this point, this point. That does not mean it is 100 0. 100 angle 0 means this is the meaning. 100 angle 90 means it comes here, like that. Okay, that is the meaning there you have to understand. Okay, so R angle theta. Okay, R angle theta volts. Okay, that is instantaneous value of the waveform. Now what we will do with this representation, we will do all the calculation like current division, voltage division, Thevenin's, Norton's. Okay, mesh analysis, node analysis, all this we will do. Okay, all this we will do. Okay, and draw the phasor diagram of the remaining components in the circuit. Once we do the remaining components in the circuit, then we project the phasor to rotate and get sinusoid. We project the phasor and rotate to get sinusoid. Yes, we project the phasor to rotate and get sinusoid. Then phasor allows us to mathematically understand phase shift or time shift. Okay, like Vm sin omega t, V1, Vm sin omega t plus 5, Vm sin omega t minus 5. So plus 5 means leading coming ahead, minus 5 means lagging coming late. Okay, that is the meaning. Then this phasor value, which is my sinusoidal quantity, can be represented in polar form, rectangular form, euler form. It can be represented in three ways. Then only calculations become easy now, sir. Okay, like for multiplication and division, polar form. For addition, subtraction, rectangular form. For other complex functions like square, square root, etc., we use euler form. Then I introduce something called J operator. See here that J is not imaginary. J is a max operator. Yes, J is a max operator in electrical engineering, which when convoluted or multiplied in frequency domain, the sinusoidal creates a phase shift by plus 90. And if you convolute or multiply by minus J, it creates by minus 90. There is a meaning. There is a mathematical meaning. Okay, like in India, 90 degrees means how much time? 5 milliseconds. Nah? Like in India, 90 degrees means 5 milliseconds. So if I convolute sinusoid by J, that signal is coming ahead by 5.5 milliseconds. And if I convolute with minus J, the signal is coming late by 5 milliseconds. That's the meaning. Then phasor relation between voltages and currents in passive elements. In register, yes, in register V equal to IR. Okay, V equal to IR. Okay, register is an in-phase element. Okay, then with that, yes, the white line is the voltage waveform, current waveform is the green dotted line, power waveform is the yellow line, and blue color waveform is the energy. Okay, now power is also actually varying quantity, but for that average power we calculate called real power or active power. And register will not create any phase shift, it is in phase element. Then average power also I derive. Then this is the phasor diagram in register alone. Unity power factor and average power or active power is Vrms into Irms facts. Okay, what is RMS today I will tell you. Then for a pure inductor, we proved mathematically that if I use sinusoidal current, voltage will lead, or with respect to voltage, current will lag. So it is a lagging element, and inductor exhibits reactance. Okay, reactance is AC resistance. Okay, and it is a lagging element. Then inductor, this white color waveform is voltage, green color is current, yellow color is power. Okay, average power is 0. Okay, energy, blue color is energy. Okay, then phasor diagram. Okay, if you rotate this phasor, voltage and current, this waveforms only you will get. This white waveform and green waveform you will get by this only. Okay, and power factor of pure inductor 0. Okay, then capacitor also we put that if I use sinusoidal voltage, current is also sinusoidal, but current will lead voltage by 90 degrees. And this is the ninth form of Ohm's law. Okay, capacitive reactance, leading element. Okay, then here again, white color waveform is voltage, green color is current. Okay, and yellow color is power, and blue color is energy. Okay, and this is the phasor diagram, power factor is 0. Okay, then yes, then we extended to what? Series RL circuit. Then we extended to series RL. In series RL, impedance concept came. Okay, in series RL, what came, sir? Impedance concept came. Okay, na? In series RL, what concept came? Impedance concept. Chalo, impedance. Yes, we studied impedance. Okay. Then impedance triangle. Okay, all mathematical, sir. Okay, don't need to by heart while doing problem. Everything we will do it. Okay. Then there are three types of physical powers. Okay, source talks about total power or apparent power in volt amperes. Register talks about real power or active power in watts, and reactive elements like inductor, capacitor called reactive power in watts, volt ampere reactives. Okay, na? Then power triangle and power factor, and this is the phasor diagram. Now, if you project this phasor diagram and rotate NASA, we get sinusoids. And we proved that in RL circuit, current lags voltage by an impedance angle phi less than 90. There is a meaning. There is a mathematical meaning we got. Okay, na? There is a mathematical meaning. Then RC circuit. Now, if you go to RC circuit, yes, if you observe this RC circuit, yes, again here impedance triangle, combination of resistance and reactance, but this is capacitive reactance now, sir, minus J operator will come. And impedance triangle, okay, then power triangle, and again phasor diagram, and we put that current will lead voltage by an impedance angle phi less than 90, and here phi is tan inverse 1 by omega c. Only notation now in RL circuit plus QL, say we say inductor absorb lagging watts, or yeah, inductor absorbs reactive or lagging watts. Capacitor generate minus reactive. See, capacitor is a sink, but minus means it is giving out like that. It is a notation, sir. Actually, nothing will generate, nothing will absorb, because this energy is oscillating from source to inductor and source to capacitor and back. But the magnetic energy, we call it as lagging or absorbing watts. The static energy, we call it as generating or leading watts. That is a notation useful for us. Then RLC circuit altogether. Yes, again, there are two types of reactance: net impedance, impedance angle, net reactive power. Okay, complete details again. Okay, net reactive power, real power. Okay, that is all same. Then only difference is, yes, though it is a series RLC circuit, but at any instant it can behave either as RL or RC or R. Okay. Then for parallel circuits, no need to again write all these things, but admittance concept. Admittances in parallel can be added. So Here, negative susceptance is inductive, positive susceptance is capacitive. Okay. From that, yes, admittances in parallel can be added. Then I gave two phasor diagrams. Draw the phasor diagram of series RLC, parallel RC, and non-canonical. This was very interesting. Okay, na? Any tough problem we can do, sir. But go satisfy KCL, KVL, Ohm's law, and go carefully. That is the meaning. Take your time, sir. Take your time to learn. Even I did not learn this subject in 1 day or 1 year, sir. It took a lot of time for me to get this level. And as a teacher at GATE level, IES level, any problem I can do. Okay, but it took so many years for me. But for you, the target is GATE exam or IES exam. And exam style, whatever limited syllabus, you read whatever content we gave and previous papers, that is enough. You need not read 100 textbooks. Don't do that right now. Target is to get good rank, good fundamentals, and be basic fundamentals in the syllabus and revise more. See, speed and accuracy will come with revision only, not one-time reading. One-time reading is more dangerous, in fact. Then I started phasor problems. See here, I gave total ammeter reading and A1, A2 I asked, but don't say 10 minus 8 is 2. Phasor difference of 10 minus 8 is 6. Phasor difference of 10 minus 8 is 6. Like, okay, then here again, yes, here again you observe now. Here also please observe. Okay. Now he gave 3 ammeter readings. He want total current, but don't algebraic addition you do. Phasor addition you do, then it is 10 amperes. Okay, na? And power factor also we got. Then this is a very simple problem. Now here voltage across inductor and voltage across capacitor are equal. That means this is under resonance. Okay, VL and VC are equal but opposite in phase. They phase cancel each other. Okay. Then yes, this was outstanding problem. That components are given, resultant are given. We need the angle. Okay. This is perhaps the first problem we learn in vectors. Okay, and also average power. Average power means active power. I told yesterday. So average power means active power because it exists only in resistor. Because the average power in pure inductor is 0 and average power in pure capacitor is also 0. Then this was very interesting problem. Okay, and IL we need to find, IR we need to find. IR is very easy, but IL was very interesting. Though I1, I2 are equal in magnitudes, but current has to flow through IL. Don't say, sir, I1 equal to I2, IL is 0. No, don't do like that. There is a voltage across passive element, current has to flow. So IL should be large enough such that I2 plus IL is also equal to I1, which is 10 amperes. That is a very interesting concept. Okay, now? Okay, chalo, now let us continue. Okay, now let us continue. Yes. Now this is a very interesting problem. Yes, some students gave me very interesting answers. Some students did do that, but let us see this. See here, problem is in this problem, V1 is a total voltage across R and L, and V2 is a total voltage across L and C. Okay, na? He did not give individual voltages. If you would have given individual voltages, na sir, happily we would have done. Voltage across RL he gave, and voltage across LC he gave. And he's asking voltage across capacitor alone he's asking. Okay. Now, the problem with this series RLC circuit is, you know, series RLC circuit can behave either as, yes, either as RL nature or RC nature or pure R nature also under resonance. We don't know. The problem here is individual voltages not given. If individual voltage is given, depending upon which is greater, we would have understood whether it is RL nature or RC nature. But he did not give. Combination voltages he gave. And moreover also, yes, and moreover also, this circuit can behave in 3 possible ways. Like that also hint to you, either RL or RC, we don't know. So that is why we have to be careful here. So now let us see this. So out of the 3 possible cases, okay, 3 possible cases. What are the 3 possible cases? We know XL greater than XC lagging power factor, XC greater than XL leading power factor, or XL equal to XC unity power factor. Yes, out of the 3 possible cases, everybody, out of the 3 possible cases, let us first rule out XL equal to XC case. Why? Because if XL equal to XC, then VL equal to VC equal in magnitude in the opposite direction. VL equal to VC equal in magnitude but opposite direction. Then voltmeter V2 reading should be 0. Please understand what I am trying to say. See, if XL equal to XC, then VL equal to VC. If XL equal to XC, then VL equal to VC. These 2 voltages are equal in magnitude and opposite in phase. The resultant voltage across L and C should be 0. Then voltmeter reading should be 0. Like you see in this problem, you see if voltage VL and voltage VC are equal, both are equal but opposite in phase, Okay, then VL plus VC should be 0. Like that here also, if that was the case, then voltmeter V2 should be 0, but it is given 9 volts. So XL equal to XC case is ruled out. But what are the other possible things? The other possible is two cases. Chalo, either lagging or leading. Now listen, sir, very interesting. Very, very interesting. Okay, chalo, let us do that now. See, first I will take case where XL greater than XC. That implies VL greater than VC. So now I am drawing the phasor diagram. So because it is a series RLC circuit, I will take current as reference. Okay, series RLC circuit, I will take current as reference. Now with respect to this current, which voltage is in phase? VR. What about VL? Because XL is greater than XC, VL should be greater than VC. VL should be greater than VC. Okay, VL should be greater than VC. Okay, VL should be greater than VC. Okay, VL is greater. Okay, what about VC? VC should be smaller. Okay, VC should be smaller. Okay, this VC should be smaller. Okay, this VC is smaller. Okay, now. Okay, now let us complete the phasor diagram with the given data. Now he said voltage across R and L is how much? V1, 20 volts. Voltage across R L is 20 volts. That means R and L. Okay, this is 20 volts. This is 20 volts. Okay, then what he told, voltage across L and C. V2 is a voltmeter across L and C is 9 volts. Voltage across L and C. Now this is VL, this is VC. Now this part of VC if you cut here, this part of VC if you cut here, this is how much he's telling, this is how much he's telling, this is VL minus VC, and he said how much? 9 volts. 9 volts. VL minus VC, that is the meaning of sir. Difference of voltage because they are anti-phase, opposite. So this part of VC if you cut here, this is 9 volts. Okay. And then altogether supply is also how much? 15 volts. Altogether supply is also 15 volts. Okay. Altogether supply. So VR we know, VL minus VC also we know, and this total is supply, which is given as 15 volts. 15 volts. Okay, now 15 volts. Chalo. Now with this data given, what is asking, sir? Is asking voltage across capacitor alone. Chalo, sir. Now very easy. Now all triangles, sir, right angle triangle. Now let us build up. I need this length. This length means this length only. See. Now in this first small triangle, right angle triangle, this is 15, this is 9. So what is this length then? This will be root of 225 minus 81, root 144 is 12 volts. VR is 12 volts. Now this is 20, this is 12. Then what is this total length? What is this total length VL? This is root of 400 minus 144, root 256 means 16. Now if total VL is 16 and difference is 9, then this length is how much, sir? This length will be automatically how much? This length will be 16 minus 9, which is 7 volt. So this length is also 7 volts. So VC is 7 volts RMS. All from triangle. Now, but see the options, sir. 7 volts is not given. 7 volts is not given. Now there is a twist in the option also. Everyone thought, arey yaar, this is not there. So most of them wrote none. Most of them wrote none, sir. But the student who is intelligent, he went to second case. What is the second possible case? Second possible case is XL less than XC. Now, if I draw the phasor diagram, again, because it is series, I will take current as reference. With respect to current, which voltage is in phase? VR is in phase. But what about VL? VL will lead I by 90, but this time XL is small, so VL is small. Yes, this VL is small. This VL is small. Okay, VC. Current will lead, voltage will lag. Okay, voltage will lag, and VC should be greater than. Okay, VC should be greater. Okay, this is VC. This is VC. Okay, now from that, let us give the data. Now see, again, VR plus VL is how much? 20 he told. VR plus VL is how much? 20. VR plus VL is 20. This is 20. Okay, then VL plus VC 9 volts. VL plus VC 9. Okay, if this is VL, okay, this is also VL. Okay, so this if you cut here, this much length if you cut here, this much length if you cut here. Okay, now, yeah, until here, this is how much, this length is, okay, 9 volts. Why it is now 9? Because VL minus VC. Okay, that means this length if you cut, this is 9 volts. Then altogether supply is how much? 15. That is VR plus VL plus VC should be 15. See, VR is here. VL plus VC is this part. Now this automatically should be how much? This should be 15. This should be 15. Chalo. Now, sir, from this data, he want total VC na. This length you want. So first find this length, add here with 9, you will get this length. So now again, all basics, sir. If this is 15, this is 9. This length is how much again? Yes, root of 225 square minus 81, root 144, 12 volts. Now automatically, if this is 12, this is 20. This length is how much? Yes. If this is 12, this is 20. This again becomes how much? Root of 256, that is 16 volts. No calculator in Genco and IS. Now if this is 16, yeah, if this is 16, obviously, yes, if this is 16, this length also will be how much? Yes, this length also will be 16. From here to here, this will be 16. Yes or no? Yes, from here to here, this will be 16. This will be 16. Okay? Yeah, this will be 16. 16. Now total VC will be how much? Total VC will be 16 plus 9 phasor addition. It is 25 volts. 25 volts. 25 volts. Okay, so that 25 volts is there in the options. 25 volts is there in the option. 25 volts is correct. See, none will be the answer if no other case exists. But here there is a case where if XC greater than XL, then that is correct. Okay, but however, XL equal to XC is not possible because if XL equal to XC, voltmeter V2 should be reading 0, na? So that case is ruled out. So here both are correct, sir. Technically speaking, both are correct. If you take XL greater than XC, 7 volts, but if you take XC greater than XL, 25 volts. But based on the options, what you have to take? 25 you have to take. Based on the options, you have to take what? 25. Please understand. 25 is the answer. 25 is the answer. Okay. Based on the option, 25 is the answer. So even in options, there is a thing that you have to understand. Okay, na? Yes. So now with all these basics of phasors, now I'm going to the next topic. Yes. Now see, sir. Suppose I take a DC voltage. Suppose I take a DC voltage. And also I take AC sinusoidal voltage. Okay. This is VAC. This is VDC. VDC. Okay. Now suppose I draw this ideal DC. Now I draw this. Like plus 10 volt. This is like minus 10. Okay. Chalo. Now if I draw this ideal DC and if I draw this ideal AC. Yes, everybody, if I draw this ideal DC and if I draw ideal AC, everybody now see here. Draw ideal DC and ideal AC. Now see here, everyone, very interesting. See, here ideal DC, yes, this is the waveform and ideal AC. Suppose if I ask what is the value of this waveform? Value of this waveform is 10 volts. Yes, this ideal DC value is always 10, no confusion. But if I ask what is the value of this waveform, that is a wrong question, sir. For this AC sinusoid, if I ask what is the value of this waveform, there is no single value. Yes or no? For AC sinusoid, if I ask what is the value of this waveform, there is a wrong question in fact. Because this waveform does not have any single value. Okay, this waveform does not have any single value. 0 is also value, plus 10 is value, minus 10 is value. Okay, plus 5 is value, minus 5 is value. Everything is a value, sir. So here I should not ask what is the value. DC is very simple, ideal DC, ripple free, always constant voltage, no confusion. Okay, but in AC sinusoid, how to determine its value? In AC sinusoid, how to determine its value? Okay, how to determine, sir, its value? Okay, how to determine its value? Okay, because there is no single value. Okay, because there is no single value, how to determine its value? Now how to estimate, how to compare, how to do all the design. So then engineers started giving some unique definition to these time varying waveforms. Because there is no single value for this AC sinusoid, then engineers started giving what, sir? Some basic definitions to understand such time varying waveforms. Okay, in that, yes, the first definition is RMS value, root RMS value or true value or effective value of a time varying waveform. Effective value of a time varying waveform. Okay, na? Okay, they started giving RMS value or effective value or true value of a time varying waveform. Okay, what is this? Now listen. Okay, because that time varying waveforms does not have any unique value. Now engineers started giving this definition. What is this definition? Yes, RMS value. Okay, yes, it is. It is that steady state value of a time varying waveform. Okay, it is that steady state value of a time varying waveform. Okay, it is that steady state value of a time varying waveform. Okay, which could also okay, it is that steady state value of a time varying waveform which could also develop, okay, which could also develop, okay, the same amount of heat, the same amount of heat, okay, the same amount of heat as given by the original waveform, okay, now original waveform for a definite period of time, for a definite period of time, okay, as given by the original waveform for a definite period of time in the circuit. Definite period of time or time period, you can say. See, it is that steady value of a time varying waveform which could also, I will say it is that steady equivalent value. Better, sir. I will again write this, okay? Better write like this. It is that steady equivalent value. This is important term. Okay. It is that steady equivalent value of a time varying waveform. It is that steady equivalent value of a time varying waveform which could also develop the same amount of heat as given by the original waveform for a different period of time in the circuit. Now see, the meanings are very interesting. See, suppose there is a network. Okay, there is a network and I'm giving some time varying voltage. You can take anything, voltage or current. Both are sources only in a sir. For example, I'm giving time taking voltage. Let us say this time varying voltage waveform is like this. Okay, now let us say this time varying voltage waveform is something like this. Okay, I am taking like a sawtooth function. Sawtooth function. Okay. Okay, I'm taking time varying waveform like this. Okay, so for this network, I'm giving time varying voltage. Okay, for this network, I'm giving time varying voltage. Okay, I'm giving time varying voltage. Okay, let us say I gave this voltage to this network for some 100 seconds. And in 100 seconds, let us say the network has developed. Okay, in this 100 seconds, the network has developed some 80 joules of heat. 80 joules of heat. Okay, so actually I'm not giving steady value. I'm giving this time varying value. And I gave this time varying voltage to this network for how much time? 100 seconds. And this 100 seconds, it has developed how much heat? 80 joules of heat. 80 joules of heat. Now, RMS value is that steady equivalent value. Yes, it is that steady equivalent value of a time varying waveform, which could also develop the same amount of heat. It is that steady equivalent value of a time varying waveform, which would also develop the same amount of heat as given by the original waveform for a different period of time in the circuit. Now, what is the meaning of this? What is the meaning? See, I am giving actually green color waveform only, which is varying 0 to k, again 0, 0 to k, again 0, 0 to k, again 0, like that it is going. Actually, it's going like this. But yes, what is RMS value? If I give this green color waveform for 100 seconds and it is developing 80 joules of heat, then similarly, if I give a steady value of voltage, similarly, if I give a steady value of voltage continuously for 100 seconds, similarly, if I give steady value of voltage continuously for 100 seconds, okay, yes, and it develops the same amount of heat in same time. That steady value is called its RMS. RMS is a mathematical idea, sir. Actually, I'm giving green color waveform only. But how much heat this green color waveform will develop in this time? If I can also develop the same heat in same time by giving a steady value, that steady value is called its RMS. It is that steady equivalent value. I will write like this. It is that steady equivalent value. Okay. It is that steady, okay, state equivalent, steady equivalent value, not state. Okay. It is that steady equivalent value. Okay. Equivalent value. Yes, it is that steady equivalent value of a time varying waveform, which could also develop the same amount of heat as given by the original waveform for a different period of time in the circuit. Now, what is the definition for RMS? So, suppose if you take voltage, yes, this VRMS will be root, okay, root 1 by T integral 0 to T voltage function square dt. Voltage function square dt. Okay, 1 by T 0 to T voltage function square dt. Volts. Okay, volts is the answer. Suppose if it is current IRMS, if it is charge RMS, if it is flux RMS, like that. Okay, if it is Vm sin theta d theta, if it is Vm sin d omega t, it's omega t d omega t, like that. Okay, that is understood, sir. Okay, now that is RMS. But always remember, RMS exists only for single parameter like voltage. There is nothing like RMS power. Okay, no, power is a product of voltage and current, and RMS is considered for a single electrical parameter like voltage or current or flux. But there is nothing like RMS power. Some books are giving wrong, sir. Okay, RMS is for a single parameter time varying value for voltage, current, flux, charge, like that. But there is no RMS power. Power is already product of voltage and current. That is different concept. But power you will write in terms of RMS voltages and currents. But there is nothing like RMS power. Okay, that confusion don't be. Okay, it is for single electrical parameter. Okay, like voltage, current, flux, charge only. Okay, now then another definition. Okay, called average value. Okay, it is called average value or mean value of a time varying waveform. Average value or mean value of time varying. Okay, again, what is the definition? Okay, it is that study equivalent value of a time varying waveform. Okay, yes, it is that study equivalent value of a time varying waveform which could also transfer the same amount of charge, as given by the original waveform, for a definite period of time in the circuit. Okay, it is that study equivalent. Okay, it is that study equivalent value of a time varying waveform which would also transfer the same amount of charge, as given by the original waveform for a different period of time in the circuit. Now, what is the meaning of this? Again, sir, suppose there is a network. Suppose there is a network, and I am giving some time varying current. Okay, again I am giving some time varying current. Okay, I am giving some time varying current. Okay, I am giving some time varying current. Okay, let us say this current waveform is something like this. Let us say this current waveform is something like this. It is time varying, it is not constant. Okay, it is time varying. So this is having minimum value, maximum value, minimum value, maximum value. Okay, so this current does not have any unique value. Okay, so I'm giving this time varying waveform to this network, and it is like this. Then what is the meaning of average value? Yes, it is that study equivalent value of a time varying waveform which would also transfer the same amount of charge. Now suppose I'm giving this waveform to this network, let us say for some 200 milliseconds. In this 200 milliseconds, this network has accumulated some 7 microcoulomb of charge. Okay, so please understand what I'm trying to say. See, I gave this time varying current to this network, say for 200 milliseconds. Okay, I gave this time varying current to this network, say for 200 milliseconds. Okay, I gave this time varying current to this network, say for 200 milliseconds, and in this 200 milliseconds, this network has accumulated 7 microcoulomb of charge. Okay, in this 200 milliseconds, this network has accumulated 7 microcoulomb of charge. Okay, now if I can also allow the network to accumulate same charge in same time by giving some study value, okay, by giving some study value, that study value is called its RMS. Suppose here it is current, I will say current, sorry, average. That is called current average. Again, I am repeating. See, RMS is heat equivalent, average is charge equivalent. Suppose I gave this green color waveform to this network for 200 milliseconds and the network has accumulated 7 microcoulomb of charge. If I can also allow the network to accumulate same charge in same time, by giving a study value. Okay, if I can also allow the network to accumulate same charge in same time by giving a study value, that study value is called its average. I am not giving this pink color waveform, sir. I am giving green color waveform only. It is varying. That current does not have any single value. But how much charge this green color waveform is giving in this time to this network, the same charge if I can also give by study value, that study value is called its average. Okay, that study value is called its average. Okay, there is a meaning now. Okay. Now, before we write average definition, yes, everybody, before we write average definition, okay, now I need to understand concept of symmetry. Yes, concept of symmetry in waveforms. Concept of symmetry in waveform. Concept of symmetry in waveforms. Okay, suppose I take a function versus time. That function is something like this. Something. Okay, it is going further. Okay, let us say it is going further. Something. Now, what is the simple meaning of symmetry? Suppose if positive area A1, yes, if positive area A1 is equal to negative area A2, yes, if positive area A1 equal to negative area A2, it's called symmetry. Like if positive area A1 is equal to negative area A2, it is called symmetrical wave. But if positive area A1 is not equal to negative area A2, then it is called asymmetrical wave. That is a simple meaning of symmetry. Okay, here I am still not talking about Fourier series, all these things, sir. I am just talking about simple meaning of symmetry. Okay, simple meaning of symmetry. Okay, here I am still not talking about okay, all these things like what happens. Okay, that part I am not talking. Okay, now that part I am still not talking. Okay, so what is the simple meaning of symmetry? I'm talking. What is the simple meaning of symmetry? Okay, like if positive area A1 equal to negative area A2, then both are said to be symmetrical. But if areas are not equal, asymmetrical. Okay, symmetrical will introduce a lot of DC components. Symmetry will never introduce DC component. We know. But in Fourier series, half wave symmetry, quarter wave symmetry, odd function, even function, that are all different, sir. That I am not talking right now. Okay. But simple meaning of symmetry is area. Area wise, you have to tell. Now I am asking a question here. Okay, I am giving current versus time. Okay, current versus time. Time is in milliseconds. Okay, current is in amperes. Suppose this waveform is like this. Okay. Zero plus 2 minus 1 2 6 8 like that. Okay, now I'm asking, is this current waveform symmetrical or not? Now I'm asking, is this current waveform symmetrical or not? Okay, is this current waveform symmetrical or not? Okay, now here positive area. If I take positive area, that is nothing but 2 amperes into 2 milli. 2 amperes into 2 milli, which is nothing but 4 millicoulomb, because product of current and time is charge, na sir. Yes, everybody should understand. Product of current and time is charge. Yes or no? Product of current and time is charge. Yes or no? See, this area of this field, because I is dq by dt, q is I into t. So I into t means area is charge. So positive area plus 2 ampere into 2 milli, 4 millicoulomb. Then what about negative area? If I calculate negative area of the function, see, again it is minus 1. Okay, modulus. Okay, we want the value magnitudes now. Areas means area is always a scalar. So magnitude -1 into what is the width here? 6 minus 2, 4 milli. So this is also 4 millicoulomb. So here positive area equal to negative area. Waveform is symmetrical. Don't see the shape. Don't see the shape. See the area. Okay, now after understanding the simple meaning of symmetry, yes, after understanding simple meaning of symmetry, so now I am declaring that, yes, now I am declaring that, yes, the average value, the average or mean value, the average or mean value of any symmetrical waveform, okay, any symmetrical waveform for one full cycle, is always 0. Okay, the average or mean value of any symmetrical waveform, please understand, the average or mean value of any symmetrical waveform for one full cycle is always 0. Okay, the average or mean value of any symmetrical waveform for one full cycle is always 0. Now they started giving this definition. Chalo. Now the right definition. First, for symmetrical waveforms. Okay. Now for symmetrical waveforms. Okay, whose positive area equal to negative area. V average. Suppose if it is voltage function, V average has two definitions. One, it is 0 for full cycle because both areas are equal, and half cycle averages they started, that is 1 by T by 2 integral 0 to T by 2 voltage function dt. This is called half cycle average. Okay, so full cycle average is 0, but half cycle. So why? Because for all symmetrical waveforms, suppose positive area equal to negative area in sinusoid, triangle, square, anything you take, if positive area equal to negative area, always average is 0. If positive area equal to negative area, always average is 0 or not? Yes, always average is 0. So to differentiate in such case, we started defining half cycle average. But important is this only, sir. This is only important. So for symmetrical waveforms, average value for full cycle is 0. Only to compare them if necessary. We are talking half cycle. But otherwise, we don't use half cycle everywhere. However, for asymmetrical waveform, asymmetrical waveform. Yes, however, for asymmetrical waveform, where positive area is not equal to negative area, yes, then we average is 1 by T integral 0 to T voltage function dt. Okay, 1 by T. This is always for asymmetrical waveform. If positive area greater than negative area, positive value. If negative area greater than positive area, negative. For asymmetrical waveform, yes, 1 by T integral 0 to T voltage function dt. That is called full cycle average. Okay, that is called what? Full cycle average. Okay, that you remember. Okay, so half cycle and we got full cycle. So generally full cycle is only 0, but for asymmetrical it is this full waveform, and if positive area greater positive value, negative area greater than negative, that means RMS is always a positive quantity, but average can be positive or negative. Remember that. Okay, then some more definitions are, then peak factor or crust factor. Peak factor or crust factor. It is simply V maximum by V RMS. Then form factor or shape factor. Okay, that is V RMS by V average. Then peak to peak value. Peak to peak value, it is simply V maximum minus V minimum. Okay, so where they will be used, I will tell you, don't worry. Okay, peak factor or crust factor is maximum value by RMS. That will give the voltage safety factors and also the insulation level safety factors. Form factor or shape factor, that are related to the performance in DC side, which I will tell you. Okay, then peak to peak value. Yes, peak to peak value is difference between maximum versus minimum. Okay, there is a peak to peak value. Okay, that is the meaning there, peak to peak value. Now in that regard, yes, now in that regard, I am writing some important note that first AC analog meters are moving iron type moving iron type, which also measure the RMS values. Which also measure the RMS values. Okay. DC analog meters. DC analog meters are PMMC type. PMMC type. Okay, and they are designed to measure average values. Okay, DC analog meters are PMMC type. Okay, and they are designed to measure average values. Okay, then rectifier type. Rectifier type meters. Okay, here actual value. Here actual value is equal to average value into form factor. Average value into form factor. Okay, so in rectifier type meters, actual value is equal to average value into form factor. Okay, in rectifier type meters, average value is, yes, actual value is average value into form factor. But here, if meter is calibrated, for sinusoid, then form factor is 1.11. 1.11. Okay, now remember, then form factor is 1. If meter is calibrated for sinusoid, then take form factor as 1.11. Otherwise, yes, you should calculate separately the form factor and take. Okay, now this information is from measurement, sir. I need this background. See, AC analog meters are moving iron instruments. Okay, digital is completely different. Digital techniques is all sampling data. Digital meters can measure average value, RMS value, anything you can press a button. Digital meters are mathematical concepts. That is signals and system sampling data. But here I am talking AC analog meters. AC analog meters are moving iron type and they are designed to measure RMS value. DC analog meters are PMMC, permanent magnet moving coil. They are designed to measure average values. Rectifier type meters, total actual value is average value into form factor. Okay, that is the meaning. Okay, then in that regard, now where to use RMS, where to use average. Now that is what everyone will be questioning. Sir, where to use? Yes, that is important. In most of our electrical engineering applications, yes, in most of our electrical engineering applications, directly or indirectly, lot of heat is generated. Okay, in most of our electrical engineering applications, directly or indirectly, lot of heat is generated. Okay, during interconversion and transmission of electrical energy. In most of our electrical engineering applications, directly or indirectly, lot of heat is generated. Okay, during interconversion and transmission of electrical energy. Hence we prefer RMS values in general. Okay, RMS values in general. Okay, example. Yes, in India. Okay, in India, for domestic supply system. Okay, domestic supply system. It is a single phase. Okay, 230 volts. 50 hertz we say. Okay, single phase. But what is this 230? 230 is RMS value only. 230 is RMS value, but it is line to neutral called phase voltage. It is line to neutral called phase voltage. Okay, na? But the actual function in our house or domestic is that V of t will be 230 root 2 sine omega, that is 2 pi f. F is how much? 50t. So the function in our house is 325 sine Okay, 314T or 100 pi. Okay, I will write like 100 pi. Okay, 100 pi T. Where maximum value in our house is 325. Okay, the waveform in our house is this. Okay, the waveform in our house is this. Okay, everybody please understand. The waveform in our house is this. Okay, the waveform in our house is this, but the RMS value is 230. Okay, now that you please understand. Okay, similarly, another example. Example in a three-phase system. Now see here, example in three-phase balanced supply. Okay, three-phase balanced supply. Okay, example I'm giving. Now we are all doing single-phase circuit analysis. Three-phase will start later. So in three-phase circuit analysis, like in India, again, if it is a power system, if power system is considered, power system. Okay, now it is a three-phase. Okay, 66 kV, let us say. Okay, 50 hertz. 50 hertz. Then the 66 kV is called what? RMS value. That is the first thing, RMS value. Actually, it is a sinusoidal waveform which is varying continuously. For that, RMS value is 66. But here it is V line to line, called line voltage. Called line voltage. Okay, like here we called, guess what? V line to neutral called phase voltage. Here V line to line. Okay, this is called line voltage or line to line voltage. Okay, like example. Okay, like example. VRY. VRY. Okay, is 66K now, sir. That is 66,000 into root 2 is maximum. Vm sine omega t will be the first wave. Okay, then Vy to B is again 66K into root 2 maximum. Vm sine lagging by another 120. Yes or no? And if I go to yes, if I go to now third waveform, VBR, that is again 600, sorry, 66 kV. Let me correct it. 66 kilo into root 2 Vm sine omega t minus 240, like that. Okay, so they are mutually shifted by, of course, omega I should write, sir. Yes, everywhere omega I should write. It is 314 or 100 pi. Better I can write 100 pi or even 314 I can write. Okay, na? So here I will write directly 100 pi. Okay, yes, here I will write as 100 pi, and here also I will write it as 100 pi, like that. Okay, that is the meaning. Here you can write minus 240 or plus 120, doesn't matter, both mean same. Okay, so that is why RMS is generally famous. But where to use average? This is important. But where to use average? However, in certain specific applications, okay, specific applications. However, in certain specific applications like battery charging, okay, battery charging, okay, electroplating, okay, metallurgical refineries, okay, electrolysis, okay, battery charging, electroplating, okay, electrometallurgical refineries, electrolysis, okay, etc. Okay, electrolysis. Another important application I will say also, like speed control of DC motor. Yes, speed control of DC motor with back EMF. Then also solar cell conversion, solar cell photovoltaic conversion circuits conversion. They are all DC master conversion circuits, etc. We use what values? Average values. Wherever charge concept is there, they're average. Okay, battery charging, you see here. Specific applications like battery charging. Okay, electroplating, electrometallurgical refineries. Okay, na? Electrolysis, speed control of DC motor with back EMF. Okay, solar cell. Okay, etc. We use what values, sir? Yes, we use what values? We use average values. That is the meaning. We use what values? Average. Otherwise, 90% everywhere we use RMS. Okay, 90% everywhere we use RMS. But in such applications, we use charge concept, that is average. Okay, na? Charge concept, that is average. Now I'll give you an example to understand this better. Suppose there is a power converter. Okay, let us say there is a power converter. Okay, okay, like phase control rectifier, PCR. Phase control rectifier will convert what? AC to variable DC. It converts fixed AC, yes, fixed AC to variable DC. Variable DC. Here DC will come. Fixed AC to variable DC. But suppose I'm selecting two applications. Okay. First application, I'm giving this to a heater. Let us say first application I'm giving to a heater. Okay. This current I'm giving to heater. Okay. This is the heater. Okay. Of R ohms. Then second application I'm giving to a battery charger. Okay. Let us say I'm giving to a battery charger. Okay. The same phase control rectifier, two applications I'm taking. One application I'm giving to heater, one application I'm giving to a battery charger of E volts. E volts. Okay. Now what is the difference? Here the power output is I square R watts. But this I is what? RMS value. RMS value. And here power output is what? E into IO. E into IO watts. This IO is called average value. Average. Okay, so please understand the difference. So I'm giving this to heater and also battery charger. But what is the difference? Heater, here heat energy, na sir, here heat is coming, here heat is coming. So which value? RMS value, because it is that steady equivalent value which could develop the same amount of heat. But here battery is charging, battery is charging. Battery is charging, na. It is that steady equivalent value which could also develop the same amount of, which could also transfer the same amount of charge. So application will decide what to calculate. So that is an important point I think. See, what I'm trying to insist is, though we know RMS definition and average definition, everybody, though we know RMS definition and average definition, but application is deciding, please understand, application is deciding what to calculate. Okay, you don't decide anything. Application is deciding what to calculate. That you please understand. Okay, application will decide what to calculate. That everyone should understand. Okay. Though we know both the definitions, but application is deciding. Okay, na? So now in that regard, everybody, now list of standard waveforms. Standard waveforms, you better by heart these things. Remember, in exams like Genco, IES, there will be no time set. Okay, standard waveforms. In the first, ideal DC waveform. Okay, if I show ideal DC, voltage versus time, it is like K volts. It is like K volts. Let us say, okay, I will take it as A volts. Okay, na? Then here automatically VRMS is A, V average is A, peak factor is 1, factor is 1. Okay, and V peak to peak is A. I will talk, sir. First, I am writing the list. You just listen to this. Later, I will explain. See, for ideal DC, RMS is A, average is A, peak factor 1, form factor 1, and peak to peak is also A. Then I am going for ideal AC sinusoid. Okay, ideal AC. Of course, what is ideal AC? Ideal AC is sinusoid. Okay, first let me write, sir. Later, I will explain all these things by expansion. So ideal AC is sinusoid. Of course, generally in radians per second is very important. Okay, radians per second. So if I show, okay, now this is plus Vm minus Vm by 2. So now in that regard, here VRMS is Vm by root 2. Okay, V average. Okay, V average is Vm by pi. Let me correct it. Here I want to write neatly. Okay, RMS is Vm. I will tell you, sir. But first, let me write the formulas. Remember, now V average. Now this is symmetrical waveform. Now average value is 0 for full cycle. 0 for full cycle. But if you take half cycle, this is 2 Vm by pi. This is called average for half cycle. Half cycle. Then peak factor. Okay, peak factor root 2. Okay, then form factor. Form factor is RMS by this now. Pi by 2 root 2 you will get. Pi by 2 root 2, that is 1.11. Then V peak to peak is how much? Peak to peak is 2 Vm, because Vm minus of minus Vm, that is 2 Vm. Okay, RMS, average for full cycle 0, average for half cycle, peak factor root 2, form factor 1.1, peak to peak is 2 Vm. I will tell sir, first listen and write down or remember, because the slides will be important for you for preparation. Then I'm coming for, yes, full wave rectified waveforms, uncontrolled full wave rectified. I'm going for uncontrolled full wave rectified. Okay, this is an uncontrolled full wave rectifier. Okay, this is an uncontrolled full wave rectifier. Okay, let us say this is something like Vm. Okay, Vm, this is like 0 pi 2 pi like that. Okay, then here VRMS is again Vm by root 2. V average is again 2 Vm by pi. Peak factor, form factor 1.11, and peak to peak is Vm. Okay, VRMS maximum by root 2, V average 2 Vm by pi, peak factor, form factor, and peak to peak. Okay, na? Then I'm giving half wave uncontrolled rectifier. Half wave uncontrolled rectifier. This is half wave uncontrolled rectifier. Okay, half wave uncontrolled rectifier. So here VRMS, Vm by 2, V average, Vm by pi, peak factor, okay, 2, form factor, pi by 2, which is 1.57, and V peak to peak is Vm only. V peak to peak is Vm only. Okay, observe sir. This is uncontrolled half wave rectifier. This is uncontrolled full wave. That is diode rectifiers. Control rectification thyristors, that part I am not teaching. That all you will learn so much in power electronics. Okay, that part I am not touching. Some things let us not interfere. Even I teach power electronics, but I should not interfere on other subjects. Okay, if you are my student in power electronics, those are different formulas. Okay, now. Okay, then after that, let us go to symmetrical square. Okay, I'm going to symmetrical square. This is also one more famous waveform. This is symmetrical wave, symmetrical square. Okay, symmetrical square. So 0 plus a minus a t by 2 t dt by 2 like that. Now here V RMS is a. Again here V average 0 for full cycle. It is a for half cycle. Here also positive area equal to negative area, now 0 for full cycle and a for half cycle. Then peak factor 1. Form factor is also 1. And V peak to peak is a minus of minus a 2a. Okay. Now I'm giving another formula here, like a function versus time. Okay. This is going to help us plot. Suppose this is function f of t in time, and this function is like this. On, little time off, discontinuous, on, off, chopped DC we call on, off like that. Okay. Here this is a. Now this is on period x and total period y. Function RMS. a root x by y function average a into x by y peak factor, okay, maximum by this root y by x, root y by x, form factor again RMS by average, that is also root y by x, and finally function peak to peak is difference, that is nothing but a only. A only. Okay, everybody. Yes, I'm sorry for yes, suddenly I had a cup of tea, sir. Actually, I was feeling very drowsy. Chalo, now listen, everybody. I'm sorry, but still, break I will give you. Just give me some time. I did not start break. Are you there? Please raise your hand, everybody. See why today's strength is slightly less when compared to average of this class. Any today any exam anything is going on? Everybody, everybody. Why? What is the reason today's slightly strength is less? Oh, okay, okay, okay. Indian overseas soil exam. Ah, you would have told such thing, na sir. Then I would have see if I would have got information. We would have taken leave. Okay. Yes, there's so many are telling exam is there. Okay, that is the reason I observe. Chalo, now everybody listen now. See again, one student asked, why can't we take our average if it is charged? See, that is what. Please understand. I told a very important point. I told a very important point. In most of our electrical engineering applications, directly or indirectly, a lot of heat is generated during interconversion and transmission. Heat is a default effector. Charge is not to be considered only in battery charging, electroplating. Their charge transfer consideration will be there. Otherwise, most of the time, heat is only considered. Okay, charge transfer consideration is only possible in such an applications where, like I told, battery charging, electroplating. But in other areas, charge is not stagnating there. Current is flowing to and fro in AC. But in certain applications, charge is transferred permanently. That is the difference you have to understand. So in such applications like battery charging, electroplating, there only we use average. Otherwise, everywhere RMS only. Everywhere RMS only. Please understand. Okay, so first I'm giving a list of standard waveforms. Okay, then you see this chopped DC. Okay, total time period is Y, conduction period is X. So RMS, average, peak factor, form factor, and peak to peak. Okay, now then based on this, I'm giving this waveform. Yes, based on this, I'm giving this waveform. Okay, based on this concept, I'm writing this. Okay, here IORMS is I naught by root 2. Okay, use this formula. Like A by root X by Y na, A is I naught, root X by Y. X is how much? T by 2 by T. It is 1 by root 2. So I naught by root. IO average, current I took, is I naught by 2. Then peak factor, root 2. Form factor, okay, is also root 2. And I peak to peak is I naught. I peak to peak is I naught. Okay, I peak to peak is I naught. Okay. Then I'm going for another important waveform, which is triangular or sawtooth. Triangular or sawtooth. Okay, this is T2T. VRMS is K by root 3. V average K by 2. Peak factor root 3. Form factor 2 by root 3. And V peak to peak is K. So RMS is K by root 3. Average is K by 2. Peak factor root 3. Okay. Form factor 2 by root 3 and V peak to peak is K. V peak to peak is K. Okay. Now remember, I want to add, sir. See this peak value wherever it occurred. See in the time period T, this peak value wherever it occurred, like it can occur at 0 or it occurred at T by 2 or it occurred anywhere here or anywhere here also, answer will be same. Remember that. I want to add that one. So Wherever the peak occur, it doesn't matter. RMS is k by root 3, average is k by 2, peak factor, form factor, and peak to peak is k. That you remember. Okay, now? Then one more last waveform. This is symmetrical triangle. These are necessary, sir, because some standard waveforms we come across in our life, and such waveforms you better remember. But beyond this, if there is any complexity, then we have to use the definition and mathematics and get it. But some standard waveforms are essential for us. Okay. This is plus k, minus k, t by 2, t. This is t by 4. This is 3t by 4. So in that regard, VRMS, okay, is again k by root 3. V average, okay, 0 full cycle, 0 full cycle. It is k by 2 for half cycle, k by 2 for half cycle. Peak factor, 3, form factor, 2 by root 3, and V peak to peak is again 2k. V peak to peak is 2k. Okay, V peak to peak is 2k. V peak to peak is 2k. Okay, na? Okay, these are some standard waveforms you better remember. Okay, ideal DC, ideal AC. Now, sir, let us just review why these answers came. Okay, let us just review. Okay, na? Because here in square wave, average value is different. Why? Because here conduction period is half, total time period is 2t. But here conduction period is x and y. That ratio is how much? Here that ratio will come 1 by 2. Okay, there is a difference. Here conduction period is x, total period is y. But here conduction period is t by 2, total period is t. That ratio is coming 2. Yes or no? There is a difference here. Okay. That this formula of 6th I applied here. Please understand. Okay. That formula I applied here. Okay, now see everybody. Okay, now let us just interpret. Now for ideal DC, sir, see for ideal DC everybody. Okay, for ideal DC, because it is already steady value, sir. It is already steady value. It is that steady value which could develop the same amount of heat. RMS, it is that steady value which should also transfer the same amount of charge. Because DC is already steady, that itself become RMS, that itself become average. Okay, na? Then peak factor, form factor, and peak to peak is here. Then for AC steady state sinusoid, okay, now see for AC steady state sinusoid, if I calculate, chalo, for AC steady state, if I calculate, okay, now see here. Now RMS, what is RMS becoming then? VRMS become, okay, root 1 by t. But what is the time period 2 pi now? 1 by t integral 0 to t function square. What is the function square? Vm square sine square omega t d omega t. That will become Vm by root 2. That is the meaning. Vm by root 2. Then we average. If you take full cycle average, na sir, 1 by t integral 0 to t function t. Vm sine omega t d omega t. This will come as 0. Full cycle average will come 0. Then to differentiate half cycle averages, 1 by t by 2. T by 2 means become pi. Integral 0 to t by 2. That is also pi. Vm sine omega t d omega t. That will become 2 Vm by pi. That will become 2 Vm by pi. So VRMS is Vm by root 2. V average for full cycle is 0, but V average for half cycle is existing. Then peak factor, form factor, etc. is the ratios. Okay, na? That you remember. Okay, that you remember. Okay, na? Then now let us understand here again. Now let us understand here again. See, for half full wave rectified, what is the average? What is RMS? VRMS is root 1 by t. Here time period is only pi, na sir. Time period is pi. 1 by t integral 0 to t function square Vm square sine square omega t d omega. That sine square theta 1 minus cos 2 theta. I think you can do these things, sir. Okay, we will do. However, I am going to practice that side. Now there, if you do, you will get this as, yes, you will get this as Vm by root 2. Now here It is however asymmetrical. So directly V average. Yes, V average is how much? 1 by T integral 0 to T function dt. That you will get how much? 2 Vm by pi directly you will get. Okay, 2 Vm by pi. Then peak factor, form factor, everything you can calculate. Okay, na? Yes, everything you will calculate. That is this part I'm talking. Now, if I go to half cycle average, yes, half cycle, this you see. See, in half cycle time period is 2 pi, but conduction period is only pi. Then VRMS will be, okay, VRMS will be root 1 by T, but conduction is only from 0 to pi, function square. Vm square, sine square, omega T, d omega. Okay, this will get it as Vm by 2. Then we average, okay, that is 1 by T, integral 0 to T, function dt, Vm sine omega T, d. Okay, that will get how much? Vm by pi. Vm by pi. Okay, Vm by pi. In VRMS, total time period is 2 pi, but conduction period is only pi. Total time period is 2 pi, conduction period is only pi. Okay, that is the meaning. That is the meaning there. Okay, now that is the meaning here. Then first this function I told you. Yes, here also for square wave. See, for square wave, positive is plus a, negative cycle is minus a. Okay. Now how to write in that case? Yes, how to write in that case? VRMS is root 1 by t. But from here 0 to t by 2 function square, it is plus a square dt. Now t by 2 to t minus a whole square dt. RMS is always positive. Okay, na? But average if you go full cycle, 1 by t. See, 0 to t by 2 plus a dt. And t by 2 to t minus a dt. This becomes 0. This becomes 0. Then they give half cycle average. 1 by t by 2 integral. Okay, integral 0 to t by 2. Okay, function dt. This will give a. This is called half cycle average. Sir, if someone asks what is the average of sinusoid 0, only you should tell. If someone asks what is the average of sinusoid 0, if they specifically ask what is half cycle average, then only you should do this. Okay, that is the meaning. Okay, na? Like, okay, na? If necessary, we can derive, sir. That is not an issue. If necessary, we can derive. Okay, na? Then for this eighth waveform also, okay, for a square I told, for eighth waveform also, see, what is the function? This function is like y equal to mx. Okay, like this function is like y equal to mx. Okay, now see, now this voltage VRMS will be root 1 by t integral 0 to t function square. But what is the function here? Function is opposite ramp, na? Opposite k by t. Okay, it is k by t whole square dt. And if it is V average, what you will get? 1 by t integral 0 to t function dt, k by dt into dt. That is average. Okay, that is RMS, that is average. Peak factor, form factor, and peak to peak. Okay, that is the meaning there. Okay, this is the ninth waveform. Okay, here also you can take and do. Okay, so we will take a break of half an hour. It is 8:50, 9:20. Come back, everybody. 9:20. Come back. Take an half an hour break first and come back 9:20. Yes, everybody, are you back? Please raise your hand. Really, some exam is there. That is why I see today so many did not attend. Some Indian Oil Corporation exam, maybe. Yes, it is Indian Oil Corporation exam. Okay, it is Indian Oil Corporation exam, maybe. Okay. Okay, now I'm continuing from where we stopped. Yes. So we learned something called standard waveforms. Now we are extending further. Yes, everybody should see now. Okay. Now let us expand. Everybody, now listen carefully. In practical, yes, in practical applications to signals and systems, okay, at signal level or communication systems and power electronics at power level, power electronics at power level, okay, in practical applications to signals and systems at signal level and power electronics at power level. Please understand this. Yes, at practical applications to signals and systems at signal level and power electronics at power level, the waveforms, okay, are neither ideal nor standard. Are neither ideal nor standard. Okay, the waveforms are neither ideal nor standard. Okay, now in practical applications to signals and systems at signal level and power electronics at power level, the waveforms are neither ideal nor standard, but mostly periodic. Okay, now then what we do? Okay, then hence we do Fourier series expansion. Fourier series expansion. Hence we do Fourier series expansion to express, okay, to express any periodic, okay, to express any periodic non-sinusoidal waveforms, okay, to expand any periodic non-sinusoidal waveform in terms of, okay, in terms of sine and cosine of higher order frequencies, okay. Yes, in practical applications to signals and systems at signal level and power electronics at power level, the waveforms are neither ideal nor standard, but mostly periodic. Okay, the waveforms are neither ideal nor standard, but mostly periodic. Hence, we do Fourier series expansion to express any periodic non-sinusoidal waveform in terms of sine and cosine of higher order frequencies. That is interesting, sir. That means circuit analysis I will teach for only two waveforms now, sir. One is ideal DC and one is ideal AC. So I teach circuit analysis for either ideal DC, that is DC steady state, and ideal AC means sinusoid. But you saw these waveforms. See, these waveforms are neither pure DC nor pure AC. Only this is ideal DC, ideal AC. Circuit analysis is DC steady state and AC steady state. But these signals are neither pure DC nor pure AC, but mostly periodic. Then how to do? We use Fourier series expansion to express any periodic non-sinusoidal waveform in terms of sine and cosine of higher order frequencies. Okay, na? So now the conclusions. Okay, conclusions from, I am writing here. Conclusions from Fourier series expansion. Fourier series expansion. Okay, conclusions from Fourier series expansion. Okay, please understand. Yes, conclusions from Fourier series expansion. So first case one. In that case one. Okay, in that first case is let some voltage function is like, okay, voltage function is like, okay, some V0 plus V1 sine omega 1t plus V2 sine omega 2t, V3 sine omega 3t, plus so on. Then V average is DC value, that is V0. V average is DC value, that is V naught. Then VRMS. What is VRMS? Root mean square of all the root means. Root of V naught square, V1 by root 2 square, V2 by root 2 square, plus so on. Plus so on. Okay. So V average is DC value V naught, but VRMS is root of V naught square, V1 by root 2 square, V2 by root 2 square, so on to infinity. Okay, that is the first case. That is the first case. Okay, now then case 2. Case 2. Now again, let some I of t is given by I naught, I1 cos omega 1 t minus phi 1, I2 cos omega 2 t minus phi 2, plus I3 cos omega 3 t minus phi 3, plus so on, let us say. Now your phase shift is also given. However, I average is DC value, that is I naught only, and IRMS is the root mean square of all the root means. Okay, here phase shift will only tell. Whether the signal is coming early or late. Here phase shift will only tell whether the signal is coming early or late. But it is same root of, this is I naught square, I1 by root 2 square, I2 by root 2 square, so on. That means phase shift will. See, here I took again Fourier series like omega 1, omega 2, omega 3, means it is Fourier series, sir. Multiple frequency Fourier series. Of course, I can write 2 omega 1, 3 omega 1 like that. It depends upon whether odd function, even function, half wave symmetry, all this you will learn. But DC value is average, root mean square of all the root means is this. However, for sinusoidal terms, maximum by RMS, maximum by root 2 is RMS, na sir. Maximum by root 2 is RMS. That is why like this. But here the difference is, I took current, but phase shift I took. That is very important. I took phase shift. Only thing to understand here is, now phase shift will not have any effect on the value. Yes, phase shift will not have any effect on the value. That is what please understand. Phase shift will not have any effect on the value. Okay, phase shift will not have any effect on the value. Okay, phase shift will not have any effect on the value. Okay, then in that case, case 3. Okay, another case, let, this is interesting, V of t is equal to V naught plus V1 sine n omega t plus phi 1 plus V2 sine n omega t minus phi 2. Okay, V1 sine n omega t plus phi 1 and V2 sine n omega t minus phi 2. Now, this is not Fourier series, sir. This is important. See, this is n omega t, this is n omega t. See, this is same frequency. Same frequency is not Fourier series. Not Fourier series. Please understand. In the previous two cases, you see, here omega 1, omega 2, omega 3 means multiple frequency Fourier series. Here also omega 1, omega 2, omega 3 means Fourier series. But here you see, yes, here you see I gave something like this, where same frequency. Now here, yes, here I should understand that first of all, V average is the DC value. If it is there, you write. Otherwise, leave it. If that V naught part is missing, then V average is 0. But if DC part exists, V average. Then what about VRMS here? You cannot directly write VRMS because these two are phasors rotating at same frequency but with phase shift. Then what we have to do? Phasor addition. Now V of t I will write it as V naught plus, this is V1 angle plus phi 1. Okay, this is V1 angle plus phi 1. And this is V2 angle minus phi 2. V2 angle minus phi 2. Now this add phasors. Add phasors. That is important. Add phasors. Okay. Now if you add phasor, okay, if you add phasor, that is V naught plus, let us say this, you will get something like Vx angle phi x. Now phasor addition, etc. we will learn as like vector diagram. We will learn. So let us say this is the DC value that I am not touching. But these two are sinusoids at same frequency. Same frequency is not Fourier series. Then what we have to do? Add the phasor. Let us say this V1 angle plus phi 1 and V2 angle minus phi 2. After adding, I got something like Vx angle phi x. Then again I will write this V of t as, chalo, this V naught. Now we added into this na, that is Vx sine n omega t plus phi x, let us say we got. Then I can write V RMS. Now I can write as root of, this is DC component V naught square, but this is the combined phasor addition Vx by root 2 whole square. So please read this again. I will explain again. Very important. This bits came, sir. Read again. I will explain. Okay, everybody sees, sir. See, the first two formulas are for Fourier series. That is not an issue. But this formula or this expansion, what the function I gave, that voltage function, these two are same frequency term. Same frequency is not Fourier series. Okay, na? That is the first thing. Same frequency term is not Fourier series. Then what to do? Add the phasors. So I added the phasor. Okay, then I got this resultant. Then I can tell RMS. Then that is a big difference here. Okay, na? So now, sir, now I'm coming to big conclusions of this, time varying waveforms concept. So electrical engineering can be divided. Yes, electrical engineering can be divided into three cases. Okay. See, these three conclusions are with respect to Fourier series. But now I am concluding in general. Okay. Now electrical engineering can be divided into three domains. Okay. 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 The basics of time varying. Okay. The time varying waveforms. Okay. Time varying waveform analysis in three domains. Okay, in entire electrical engineering is classified into three domains, three cases. Okay, what are they? Case one, this is called sinusoidal supply. Sinusoidal supply to linear load. Now, sinusoidal supply to linear load, which subjects will come there? Yes, which subjects will come there? Like electrical circuit analysis or network analysis. Okay, na? Now here, let V of t is equal to V sine omega t plus theta volts. Okay, na? Plus theta volts. I is equal to some I sine omega t plus 5 amperes. So that is why in circuit theory there is no Fourier series requirement, because ideal sinusoid only we do, and for linear also, linear components. Okay, sinusoidal supply to linear load. Okay, let me write neatly. Sinusoidal supply to linear load. Okay, sinusoidal supply to linear load. Okay, which subjects come here? Which subjects come here? Like electrical circuit analysis or network analysis will come here. Okay, na? Yes, in that, yes. Then in that case, okay, then in that case here, real power is simply Vrms into Irms cos of theta minus 5 watts. Reactive power, Vrms, Irms sine of theta minus 5. Total power, Vrms into Irms. Okay, then power factor. Power factor here is cos 5. That is simply P by S. Okay. Okay, I will write neatly. Total power factor of power factor. Okay, power factor is P by S. P by S. If I do the P by S, it is cos of phi. Here, phi is the phase angle between voltage and current, but voltage is having already with reference theta and current is having phi. So difference will become theta minus phi. Theta minus phi is the overall phase, like that I took. Okay. Of course, this is in volts, this is in amperes, this is in watts, this is in wars, this is in VAs. Okay, and these are the things. So this is our case where sinusoidal supply to linear load means ideal AC with RLC network. Okay, ideal AC with the RLC network. Okay, that is the meaning. Sinusoidal supply to linear load. Okay, this is ideal AC to RLC circuit. Here I took purposefully V at theta, I at phi only to show the difference. That means with respect to common reference, I am comparing them. To show the difference, I am showing like this. Actually, you can take V as angle 0 and I as phi, then difference will become phi only. But to show like a formula and difference, I am taking like that. Okay, let us say with respect to some common reference, V is given at plus theta and I is given at plus phi, and the difference is theta minus phi. That is the concept here. Okay, just to write like a formula. Then case 2. Case 2 will come. This is non-sinusoidal. Non-sinusoidal supply to linear load. Okay, non-sinusoidal supply to linear. Non-sinusoidal supply to linear load. Okay, this is non-sinusoidal supply to linear load. Okay, let. Okay, now let. If it is non-sinusoidal supply to linear load, let. Now in that regard, what you do? Because supply itself is non-sinusoidal, we get Fourier series. Supply itself is non-sinusoidal, we get Fourier series. Yes or no? Then in that case, yes, V of t will be V naught V1 sine omega 1 t plus theta 1 V2 sine omega 2 t plus theta 2 plus V3 sine omega 3 t plus theta 3 plus so on. And also current I of t is also I naught I1 sine omega 1 t plus some phi 1 fundamental component, I2 sine omega 2 t plus phi 2, I3 sine omega 3 t plus phi 3 plus so on. Okay now. Then I can say real power. Okay, that is DC component V naught I naught. Then fundamental to fundamental V1 RMS, I1 RMS, cos of angle theta 1 minus phi 1. Then V2 RMS, I2 RMS, cos of angle between theta 2 and phi 2. V3 RMS, I3 RMS, cos of angle between theta 3 minus phi 3, plus so on. Okay. V1 RMS, okay, like that we can do. Then reactive power. Reactive power is never for DC component, it's only for AC, but fundamental to fundamental. V1 RMS, I1 RMS, these conclusions are very important, sir. Sin theta 1 minus phi 1. Then V2 RMS, I2 RMS, Sine of angle between theta 2 minus phi 2. V3 RMS. V3 RMS. Sine of angle between theta 3 minus phi 3. Plus so on. Plus so on. Okay. Then total power. Doubts you ask at the last, sir. Yes. Observe. See, I'm not writing just for fun, sir. Here in online, we need to suppose to write everything. And notes should be pakka at least. Now, total power. Total power is simply V total RMS into I total RMS. Now, V total RMS, we know it is root of V naught square, V1 by root 2 square, V2 by root 2 square, so on it will go. Okay, so on it will go into I total RMS. This is I naught square, I1 by root 2 square, I2 by root 2 square, plus so on, plus so on. Plus so on. Okay, na? Okay. Of course, here this is in volts, this is in amperes, this is in watts, this is in bars, and this is in volt amperes, VS. And now here power factor is P by S. And because there is no single impedance angle or single phase angle, as it is Fourier series, it is simply the ratio of equation 1 by equation 2. Equation 1 is this equation P, and equation 2 is this value, which is 2. So we have to indirectly calculate total real power and total power, apparent power, and then that ratio will give power factor here. Very, very important fundamentals. I will do such Gate and IS bits, sir. You be ready. Then case 3 is more interesting. This is case 3, which is sinusoidal supply to non-linear load. Sinusoidal supply to non-linear. Sinusoidal supply to non-linear load. Let supply is sinusoidal. So this will be, I will write like this, V1 sine omega 1 t plus theta 1. This I will write like this. Actually, sinusoidal and no Fourier series, because Fourier series of sin x is sin x only. So this is same. But because load is non-linear, now this is like power electronics. This is like power electronics. This case is power electronics or even analog also. Previous case, this is for signals and system. This is signals and system case. Signals and communications. Signals and communication. Okay, that case. I will write like, okay, this is signal and communication. I will write like COMM, communication. Okay, na? Then this is sinusoidal. Though you are giving supply pure sine, but load is non-linear. Which are non-linear loads which does not obey Ohm's law? Which are non-linear loads which does not obey Ohm's law? That means thyristor-based circuits, diodes-based circuits, etc. They are all non-linear. Okay, na? In that regard. Chalo, in that regard, if I go. Now here, voltage is sinusoidal, so no Fourier expansion, but current is different. Now if you go to current, yes, if you go to current. Now here, let us say it is I0, I1 sine omega 1 t plus phi 1, I2 sine omega t 2t plus phi 2, I3 sine omega 3t plus phi 3, like that it is going, let us say. Then I can say real power. Fundamental to fundamental, because these products will become zero, only fundamental. That is V1 RMS into I1 RMS cos of theta 1 minus phi 1. Reactive power. V1 RMS, I1 RMS, sine of theta 2 minus phi 2. Sorry. It is sine, but same. Fundamental to fundamental you are taking. I will argue, sir. If anyone having doubt, I will explain also. But this background you will get from different subjects also, sir. Then total power. Here V total RMS into I total RMS. V total RMS because it is sinusoid, that is V1 by root 2. Now I total RMS is what? I naught square I1 by root 2 square I2 by root 2 square. So okay, okay. So we get this. Okay now. So now here total power factor. Now this is different. Here power factor is P by S. P is what? Only fundamental because pure sine, but I is fundamental to fundamental cos of theta 1 minus phi 1. But when it comes to total power, V total RMS is only this because it is pure sine, but I total is including harmonics. I naught square I1 by root 2 square I2 by root 2 square plus 1. Now if you remove these unnecessary things, yes, if you remove these unnecessary things, yes. Now I will say this power factor. Okay, this power factor will be I1 RMS. Here I will write I1 RMS. That means RMS of fundamental component only because I1 by root 2 by this total is I total RMS. I total RMS into this value is still there. That is cos of theta 1 minus phi 1. So this is called as total power factor. Total power factor. This is called distortion factor. Distortion factor. Specifically telling current distortion factor. Okay. Current distortion factor. This is called fundamental power factor. Fundamental power factor or displacement power factor or displacement power factor. Important terms are this is current distortion factor, this is displacement power factor or fundamental power. That is very, very, very interesting that you have to understand. So now this ratio of I1 RMS by I total RMS is less than 1 and this also is less than 1. So less than 1 into less than 1, total power factor is horrible. That is why in power electronics, total power factor is much low. Okay, please understand that. Total power factor is much low. Okay, na? Okay, just go through these cases, everyone. Case 1, sinusoidal supply to linear load, circuit theory. Case 2, non-sinusoidal supply to linear load. So though load is linear, supply itself is non-sinusoidal, like triangular or square. Then sinusoidal supply to linear load. However, this is in volts, this is in amperes, this is in watts, volt ampere reactives, and this is in VAs, volt amperes. Okay, and this is distortion factor, displacement power factor. Okay, fundamental power factor is called displacement power factor, DPF. Okay, displacement power. So go through this, sir. I will explain again. Go through this. Okay, everybody. So this is very, very interesting, sir. Okay, very interesting. Higher order frequencies in Fourier series. What is the meaning of higher order frequencies? You will express, see, suppose in India, 50 hertz is fundamental. 3 times fundamental, 3 omega t, 150. 5 times fundamental, 5 omega t, 250 hertz. 7 times fundamental, 7 into 50, 350. That are all called higher order frequencies. The secrets come from Fourier series. See, if you don't have knowledge on Fourier series, then it is difficult to understand. But Fourier series you will learn in maths, and also you will learn in signals and systems. So Fourier series will expand any periodic non-sinusoidal waveforms in terms of sine and cosine. Okay, that is the meaning there. That is the case. Same frequency means if that case is given, then we have to do like that I told her. If Fourier series is given, we told her. But if say, a problem comes with same frequency terms, then you be careful that you don't mistake it as Fourier series is the meaning there. See, some students are telling today CDF means current distortion factor. Pandey, CDF means current distortion factor. VT is fundamental and IT Fourier series, it has, that is third case only. That itself is third case only. VT fundamental means it is only the pure sinusoid only will have that. No Fourier series expansion. That is the meaning there. Okay, that is the meaning. No Fourier series. And what is this today class timings? You are telling 1 p.m. to 10:30 p.m. What is this? Anyone? That anonymous attendee, I told you, please write your name here. Anonymous attendee is a very wrong. I don't want to entertain such people actually. I told 100 times. Now, what is the meaning today? Class timings is from 1 p.m. to 10:30. You are writing. What is the reason? Which class is from 1 to 10:30 p.m.? Anyone? Anyone tell me which class is from 1 p.m. to 10:30 p.m. today? See, so many are telling no class, but who told that the class is from 1 p.m. to 10:30 p.m.? No class. Okay, no class. Then I will go up to 11. Okay, let us go up to 11 because for me 11:30 onwards some other class is there. Okay, then I will go slowly up to 11. Is it okay for you? Okay, I will go. I will go cool, sir. We will go cool. Okay, see, but you see all these people who are writing here. See Rohit, Imtiaz, Yogesh. See one anonymous attendee. What is telling you? See that today class is from 1 p.m. to 10:30 p.m. What is this, sir? See, some people now, they who is this? That is why they don't put the name also, sir. That is a problem with them. Okay, chalo, let us forget. Let us go positive. Okay, chalo, now see here. Okay, so these cases you have to remember, sir. See, first Fourier series cases are different. Don't confuse. This is from Fourier series conclusion. Fundamental, second harmonic. Then V average, VRMS. Current also Fourier series, IR average, IRMS. Phase shift will not have any impact. Then if same frequency terms come, yes, if same frequency terms come, then it is not Fourier series. Then in such case, don't misunderstand, but add the phasors first and then we will come to RMS. That is the meaning. Then the big difference, but the big discrimination about all the three cases in electrical is, yes, sinusoidal supply to linear load, non-sinusoidal supply to linear load, and sinusoidal supply to non-linear load. Okay, all these cases. CDF means current distortion factor, DPF means displacement power factor, which is also called fundamental power factor. Okay, now. So now with all these basics, now I'm going to the question. So IES object. Power absorbed by 3 ohm is dash. Okay. Now to the 3 ohm resistor. Current is going in this resistor. And this current waveform is something like this. Time in milliseconds. And this current is in amperes. This is 0, 2, 4, 6 like that. 6 amperes. 6 amperes. Okay, 6 amperes. So 1 minute answer, everybody should answer. Okay, see, this is resistor Nasar heat problem. Na? See, power absorbed by 3 ohms. But it is resistor Nasar. If it is resistor, heat will come. Yes, heat will come. Then power absorbed is I square R. But here heat na I RMS square into R. Yes, I RMS square. See, for this waveform, we already gave the shortcut. What is the shortcut I told you? Okay. See, for this waveform, the shortcut I told here. Okay. Yes, I told here. See here, everyone. Yeah, k by root 3 na RMS is k. K is the maximum value by root 3. Okay, na? Like that, k by root 3 we can take. Okay, so this is k by root 3. K is what? 6. 6 by root 3 is RMS. RMS square into R. R is also 3. So this is 36 watts. 36 watts. Suppose you don't remember that formula, then you can do. See, if you don't remember the formula, then what to do? Yes, this IRMS will be root 1 by t. What is the time period of the waveform? 2 milliseconds. Now milli don't need to write, sir. If you take milli, integral 0 to 2 milli also you have to take. So don't waste that. So in 1 by 2 time period, don't take milli. Some books will take. If you take milli again, you have to integrate from 0 to 2 milli, and that milli will cancel. Waste of time. So 1 by 2 integral 0 to 2 function square. What is the function slope? Opposite 6 by adjacent 2. Opposite 6 by adjacent 2. It is 3t square dt. If you do that also, you will get this as 6 by root 3 amps only. You will get that. The meaning. In case you don't remember, you have to do like that. Okay, na? So now this is a gate bit, sir. Gate 2 marks. Again, power absorbed. Okay, power absorbed by 2 ohms is dash. Okay, power absorbed by 2 ohms is dash. This is 10 volts. 2, 4, 6, 8, 10 like that. So power absorbed by 2 ohms. Okay, this is power absorbed by 2 ohms. Okay, power absorbed by 2 ohms and time in seconds only. Now here there is no shortcut. See, for this trapezoidal waveform, I did not give any shortcut. Yes or no? Yes, please understand. For this trapezoidal wave, I did not give any shortcut. So let us define the function for one full time period. But here also power absorbed in resistor Nasar heat. Heat means Vrms square by R. Here the function is voltage. So Vrms square by R. But this is a trapezoidal function which I did not give any formula. So let us define. See what is the time period of this function? Like 4 seconds. Let us define the function for one full time period. First from 0 to 2 seconds. From 0 to 2 seconds, yes, everybody, from 0 to 2 seconds, this function is like y equal to mx. Na? Slope is how much? 10 by 2. Okay, 5t. Then from 2 to 4, voltage function is constant 10. Voltage function is constant 10. Okay, this voltage function is constant 10. Okay, so now once you know this, then Vrms is root 1 by t integral 0 to 2 function square 5t square dt integral 2 to 4 function square 10 square dt 10 square dt 10 square dt. Now if you expand this, sir, yes, that was gate question. Of course, calculators allowed. You will get this as 8.16 volts. Then I can say then power absorbed is Vrms square by R. Vrms square by R. That is 8.16 square by R. R is how much? 2. Okay, this will get 33.33 watts. 33.5. Observe, sir, very interesting model. Okay, very important model and interesting model. Okay, that is what you have to understand. That is very important and interesting model. Okay, now everybody. Yes, now I'm going to another model. This is a general question which is given in IES conventional. Just observe. Find VRMS, V average, peak factor, form factor, and V peak to peak. VRMS, V average, peak factor, form factor, and V peak to peak. So in that regard, what happened? Voltage function versus time, and this is the function I'm giving. This is time in microseconds. This is time in microseconds. Okay, this is now 20 volts here plus 20 volt. This is like minus 4 volt, and this is like 4 micro, 6 micro, 8. Okay, again 12, 14, 16, 20, like that it goes. Chalo, I need VRMS, V average, peak factor, form factor, and also peak to peak value. Okay, and I also need what? Peak to peak value. Okay, that is what I want. Okay, so now in that regard, everybody. Yes, in that regard, if you observe, yes, if you observe carefully. Now here, what is the time period of this function? Time taken to repeat itself. Okay, it is time taken to repeat. So until here, okay, until here it is time period. So time period is 8 microseconds. So let us define the function for one full time period, because this is a asymmetrical and discontinuous answer. So yes, first if you define from 0 to 4 micro, yes, 0 to 4 micro, voltage function is constant, which is 20 volts. Then if I go from 4 micro to 6 micro, 4 micro to 6 micro, now this point is like 6 comma minus 4, this point is like 4 comma 0. 6 comma minus 4, 4 comma 0. So if you do that, y minus y1, y minus y1 is m. M is how much? y2 minus y1 by x2 minus x1 into x minus x1. So y-axis is voltage axis. This is minus 4 by 2, minus 2. So this is minus 2t plus 8. Minus 2t plus 8. And then 6 micro to 8 micro. However, voltage is 0. Voltage is 0. So we define the function for one full time period, sir. See, time period here is 8 microseconds. 0 to 4 is a constant. So V of t is 20. 4 to 6 is a negative ramp with positive intercept. So minus 2t plus 8. And 6 to 8 micro is 0. So once we defined here, now VRMS. VRMS is root total 1 by 8 micro. You need not take micro. First from 0 to 4 function square. 20 square dt. Okay. Yeah, 20 square dt Okay. Then 4 to 6 is minus 2t plus 8 square dt because we got this function plus 6 to 8 function square, that is 0 square 0 square, that many volts will, many volts will. We average 1 by t integral 0 to 4 function dt constant na 20 dt 4 to 6, no need to take micro, sir. If you take micro here also you take micro, that will cancel. Minus 2t plus 8 dt 6 to 8 function dt 0 volts. Now if you calculate, see, actually this is an IS conventional, everybody See, I was talking with your schedule manager. Everybody, yes, everybody, raise your hand. See, he will again call me because he's also looking that you told some of you told that today last class for your other subject, but your some students are telling sir no class today. But I don't know. I asked him. He will tell the schedule. I think he will call me again in few minutes. Okay. Then again I will talk with him. Tomorrow I am planning to take if other subjects started also. See anyone describe me. See, anyone describe me tomorrow? There is no other subject. Huh? Today is the last class for some subject you told. Is it true? Anyone tell me? You keep writing in this question answer. Which subject last class you are telling? EMT last day today. Okay, EMT last day today. And tomorrow schedule is what? Nothing is announced. My subject only is there, right? Okay. So tomorrow nothing came. See, one thing, my subject will be there. That is for sure. Okay, we will update that. Okay, my subject is there. Okay, na. But what will be there tomorrow afternoon? I told Seshu, the schedule manager. If there is second subject also, I will confirm you. Okay, he told that he will call me in few minutes. Okay, okay. Tomorrow nothing came. Network also not updated. Yes, I know. Malavika, I know network not updated, but we will update that. That is what I told him. Tomorrow network pakka, sir. That is from 7 to 1 or 7 to 11 pakka. Okay, 7 to 11 minimum it will be there. Even for me, Sunday, tomorrow, other batch where I'm lagging, I need to take more hours. Something we will do. But what about the second subject he will announce now? I will tell you in few minutes. He will call me again, then I will again interrupt. Okay, now? Chalo, okay, let us continue now. Let us continue. So now see here. Here after calculation, see this is an IES conventional problem, sir. This is an IES conventional problem. See after calculations, yes. In case here some students did it, sir. But here after calculations, you will get this. Okay. VRMS you are getting 14.18 volts. Okay, V average you are getting 9.5 volts. Then I am continuing peak factor. Peak factor is maximum by RMS. Okay, maximum is how much? 20 by RMS 14.18. Okay, that you will get it as 1.41. And then form factor. So if you go to form factor, that is VRMS by V average. There is nothing but 14.18 by 9.5. You will get this as, okay, you will get this as 1.49. Okay, and finally V peak to peak. V peak to peak is how much, sir? See, this is 20 minus of minus 4. Okay, 20 minus of minus 4. It is 24 volts. 24 volts. Okay, see these answers, everybody. See these answers. Okay, na? Okay, then I'm going to, this is excellent question, sir, which was given in gate. Okay, this is a question given in gate 2 marks. Okay, total power absorbed by the battery. Total power absorbed by the battery. Okay, this is a battery charger. Which is charging a battery. AC to DC. This is a 12 volt 2 ohm battery. Now what is the meaning of 12 volt 2 ohms? 12 volt 2 ohms. The meaning of 12 volt 2 ohms is, please understand, the meaning of 12 volt 2 ohm is, yes, the meaning of 12 volt 2 ohms is, it is a practical battery with internal resistance. Okay, it is a practical battery with internal resistance. That is the meaning. It is a practical battery with internal resistance. Okay, it is 12 volt 2 ohms. Okay, it is a practical battery with internal resistance. Okay, now so then this charging current he gave like this, sir. This charging current he gave like this. This charging current in amperes he gave like this. So this is 2 ampere, 5 ampere. So this is now 3, 5, 8, 10, 13 in milliseconds. Okay. So there is a practical battery charger which is converting AC to DC and charging the battery. Okay. And there is a time varying current which is flowing through the battery. Now is asking total power absorbed of the battery. Okay. Very, very interesting, sir. Okay. So I'm giving you 2 minutes. Try something. We'll close in a few minutes, sir. But please, little patience. Okay. Tomorrow schedule also I'm going to call him, but try something. 2 minutes, everybody. Gate questions, sir. I want everyone to do this. Okay. See now. See again, sir. This is a waveform where it is neither standard nor the list of formulas I give. Again, let us define. And moreover, see, it is a practical battery with internal resistance. Now, that concept is important. Now, if it is a practical battery with internal resistance, see the meaning. Okay, it is a 12 volt and 2 ohms. That is very interesting. So, this is 12 volt. Yes, 12 volt. And this is 2 ohm. And the charging current is flowing like this. The charging current is flowing like this. Now, you know, this part is charging, this part is charging, and this part is heat losses. This part is heat losses. Then total power absorbed by the battery is, one is 12 into I and one is I square R. I square R. I square R. 12 volts into I square. But see the difference, sir. Because here for battery discharging, here we should calculate what average value. And for resistor loss, heat will occur na practical battery. Yes, that is heat na, so RMS value. That means for the same current waveform, see how beautiful problem it is. For the same current waveform, we need to calculate both RMS and as well as average. Okay, now for the same current waveform, we should calculate both RMS and average. So now let us calculate that. First, let us define the function for one full time period. What is the time period here? Time period is 5 milliseconds. Na? First from 0 to 3 milliseconds. From 0 to 3 milli. Okay, this current function I of t is like y equal to mx plus c. Slope is how much? Opposite by adjacent 3 t. T plus intercept is 2. You can take 2-point formula, sir, but directly slope, this is opposite 5 minus 2, 3, adjacent 3. Slope is 1, intercept is 2, t plus 2. And however, from 3 milli to 5 milli, yes, from 3 milli to 5 milli, what is the current function? Current function is constant. Current function is constant, which is 2. Which is 2. Current function is constant, which is 2. Okay, current function is constant, which is 2. Okay, na? That is what exactly happening. So that is t plus 2 and this is 2. Okay, now once you know this, once you know this, yes, what is IRMS? Yes, what is IRMS? If you go with IRMS, okay, yes, root, okay, this is 1 by t, 1 by 5, integral 0 to 3, okay, 0 to 3, function square, t plus 2 square dt, yes, 3 to 5, function square, 2 square dt. That will be RMS. And if you take I average, 1 by 5, 0 to 3, function dt, plus 3 to 5 also function. It is constant function dt. Now you expand both. This you'll get IRMS, yes. If you expand both, na sir, yes, if you expand both. RMS you will get 3.06 amperes and average you will get 2.9 amperes. Now conclusion. Now conclusion. Yes, I am now bringing these conclusions here. Okay. Yes, now conclusions. Then power lost is one is 12 into average 2.9 and one is IRMS square, that is 3.06 square into R2. So this will get it in 2 parts. Okay, this will get it in 2 parts. One is 34.8, one is 18.72. Altogether 53.52 watts. 53.52 watts. That is the meaning. 53.52 watts. Okay, that is a very, very interesting question. Okay, that is a very. So I will take up doubts today. Yes, everybody doubts. Please ask doubts. Anyone doubts? Yeah, Imtiaz. Yes, please go ahead, Imtiaz.
Good morning, sir.
Tell me, Imtiaz.
Sir, in today's first problem, sir.
Okay, tell me.
Sir, in this case, he's not mentioned any lagging or leading, no, sir.
Which one?
Today's first problem, homework problem.
Oh, okay. That is why it is not mentioned. That is why I took both cases. See, because it is not mentioned as lagging or leading only, that is why I took both cases and we did that.
Yes, sir. Sir, if in case both answers 7 volts and
that is what. See the trick here. Actually, both are correct answers. 7 is also correct. 25 is also correct. But based on the options, you have to take 25. But to do that 25, an intelligent student has to go even leading power factor case and do it.
Yes, sir.
But none will be the answer. See, none will be the answer only if no other case exists. But actually, for leading power factor, 25 exists. So based on the option, 25 is the correct answer.
Sir, my doubt was, if in option have 7 volts also there, then at the time it will select 25 or 7.
That is actually both become MSQ. Today now MSQ is then a multiple select question.
Yes, sir.
That will be in IES. I will tell you the trick. In IES, such problems always in UPSC key first one is given. Suppose in options A, B, C, D, A is first. Correct. Then A is the correct. That is a UPSC. I don't know why they follow that. Actually, both are correct answer. But here, based on the option, I am declaring which is correct. But as you said, if both are there, like both are correct, in GATE they will give full marks. And
okay,
MSQ. But in IES, you see some old bits in IES. If answers are there, that is actually mistake in IES. But they generally give answer for the first option. Here is correct.
Okay, sir.
Okay, na?
Sir, sir, one more, sir. Sir, as in last problem, means we are starting from the power absorbed by 2 ohm resistor is there, no, sir?
Yes.
Sir, can you do as a triangular plus rectangle square?
Yes, you can do. But that method I am not teaching because that cannot be uniformly applied to every problem. That cannot be applied uniformly to every problem. This is a distance.
Yes, sir.
You cannot apply here. That trick in this case may be applied.
Okay, sir.
That is why I am not teaching certain things, because it is not applicable everywhere.
Okay, sir.
Okay, na?
Sir, one more, sir.
Okay.
Sir, as we case 3 is there now, sir. Can we have a case for V of t as a Fourier series and I of t as a normal fundamental?
It is not possible. Now, see, response is always current. Excitation is voltage always.
Sir, means non-sinusoidal supply and non-sinusoidal means non-linear load.
That also comes under, see, no, that also comes under to this only. If you take a non-sinusoidal supply and also non-linear load, also both Fourier series one, that means indirectly this case only will come.
Sir, but the heading was there non-sinusoidal plus 2 linear load.
Because that is a part of it. That is a part of it. See, if supply itself is non-sinusoidal, let the load be linear or non-linear, it doesn't matter. It will come to this case only.
Yes, sir.
That is why, a mathematical point of view, these are the only 3 cases. But not, see, one way non-sinusoidal to non-linear, it is only communication. Communication power analysis we never do. Now power factor, all this we never calculate. That is why also in books they don't give that.
Okay, sir.
And in power level, we are famous with Fourier series and also sinusoidal only.
Okay, sir.
Okay. Right.
Thank you so much, sir.
Yeah. Vinita.
Sir, my doubt got clarified, sir. The combination of triangle and rectangular signals.
You can do, but that is not applicable to all. See, such tricks I stopped because I was teaching initially, but students started applying everywhere and there is no definite rule that where to apply, not to apply. Actually, that way, I had seen all the books in the world, but there is no definite rule where to apply, where not to apply.
Yes, sir.
That is why I stopped teaching such. Unnecessary students are trying, and some areas it is failing.
Okay, sir.
That is why I stopped that. See, in books also, sir, if such tricks are unique, everyone would have written in the books also.
Yes, sir.
That is the reason I am stopping. Even suppose negative, see, that was a positive waveform. See, as one of your friend mentioned, see, it was a positive waveform. That is why here it is possible. Here it is possible. But if it was a negative waveform, then it is not possible, right?
Yes, sir.
Yes, that is the reason. Okay?
Okay, sir.
Okay.
Thank you, sir.
Right. Yogesh?
Hello, sir.
Tell me, Yogesh.
Sir, actually, I had a problem in day before yesterday's one problem, sir, we have solved on that this similar capacitor rating, sir.
Tell me, what is your doubt? Tell me. Yeah, understood. Tell me.
We have solved that Q max is equal to C total into V max, na, sir. Sir, that V max means we have to not take that 5 volts, sir.
No,
because
see, when the voltage itself is declared maximum is 10/3, you cannot give 5, because if you see, this itself will come 10/3 maximum voltage. Yes or no?
Yes, sir.
If you give 10/3,
in series, both capacitors can block 5 volt, no, sir.
Both no. That is the problem. See, no, if that was the case, then answer would have been 5 volts, na.
Yes.
In capacitors, if they were similar rating, then your answer is correct. Yeah. Suppose, see, this is 2.5 micro, 2.5 volt, 2.5 micro, 2. Then similar ratings, then answer is 5 volts. Suppose this is 2.5 volt capacitor, 2 microfarad. This is also 2.5 volt capacitor, 2 microfarad. Then this total will block 5 volts.
Okay.
But they are dissimilar now. One is 2 micro, one is 3 micro.
Yes, sir. Yes.
So in capacitor, voltage division is inversely proportional to capacitance. So smaller capacitor will charge first.
Yes, sir. Yes.
And that there the limit is only 10/3.
Yes, sir. Yes. Got it, sir.
Very good. Right.
Thank you, sir. Thank you.
Sweta?
Yes, hello, sir.
Tell me, Sweta.
सर आरएमएस वैल्यू की डेफिनेशन में जैसे सर उसमें यूं आपने बताया ना कि आरएमएस वैल्यू एक से स्टेडी वैल्यू होती है, तो सर जैसे मतलब एक वो कांस्टेंट वैल्यू है और जो नेटवर्क होता है उसमें एलसी कंपोनेंट्स रहते हैं, तो जब मतलब एक कांस्टेंट वैल्यू देंगे तो वो तो
ये इक्विवेलेंट मैथमेटिक्स नहीं, ऐसा इरादा नहीं है इसका। ये मतलब होगा कि हीट लॉस कौन करेगा? अगर आइडियल इंडक्टर आइडियल कैपेसिटर तो उसमें तो लॉस नहीं रहेगा।
यस सर।
तो उस हिसाब से भी देखें तो लॉसेस किसको होगा? रेजिस्टर को ही हो गया ना।
यस सर।
लेकिन
ठीक है,
मैथमेटिकल इक्विवेलेंट कॉन्सेप्ट है। इट इज अ स्टडी स्टेट इक्विवेलेंट, इट इज अ मैथमेटिकल इक्विवेलेंट बट नॉट फिजिकली गिविंग।
ठीक है सर।
ठीक है, अगर उस हिसाब से भी देखे तो वो रजिस्टर ही लॉसेस करेगा, तो हीट लॉस रजिस्टर को वो स्टडी वैल्यू लेंगे और इंडक्टर कैपेसिटर को नेग्लेक्ट करेंगे, सेम मीनिंग.
Yes sir, now got it.
Okay.
Yes sir. Sir, one more doubt.
That is the real power is a convertible part or utilizable part which is given only for register component actually.
Yes sir.
So register in the world will not only create loss, but register in the world will model all the physical interconversion part of energy like heat energy, sound energy, light energy, or mechanical energy. Like आप electrical हो, ट्रिपली हो आप.
Yes sir.
एक एग्जांपल बताता हूँ, देखो ट्रिपली में आपको इक्विवेलेंट सर्किट ऑफ इंडक्शन मोटर मालूम है?
नहीं सर, इलेक्ट्रिकल की हूँ मैं.
No, you are electrical only ना.
Yes sir.
You know the equivalent circuit of three phase induction motor?
सर इंडक्शन मोटर हुआ नहीं है अभी.
हाँ ठीक है, वो इक्विवेलेंट सर्किट में मैकेनिकल पावर रजिस्टर को ही निकाल कर that R2 by SI से निकालेंगे ना.
Yes sir, yes sir.
That means even mechanical power what is developed in motor is also modeled in terms of register only.
Yes sir, I got it sir.
Okay, right.
Yes sir, one more doubt sir. सर जो एग्जांपल लिया था 3 फेज बैलेंस सप्लाई वाला 66 kV. सर इसमें जैसे जो मैक्सिमम वैल्यू होती है उसको RMS into √2 करके लिखते हैं, तो मतलब सर ये VM क्यों लिखा है हमने यहाँ पे?
Oh yeah. Thank you. This VM 9 लिखना है मुझे.
अच्छा फिर ठीक है सर.
VM होगा. Yes.
Okay sir.
That's good. At least notes will be correct now. वो VM ही ये होगा. That 3 वो VM के प्लेस में ये आएगा. That is my intention. Actually my intention वो VM के प्लेस में ये आएगा.
Okay sir. Thank you sir.
Right.
Yes.
Right. So tomorrow schedule will come, sir. You wait. I think you have to. But the schedule manager is trying. But definitely there will be utilization of time. If nothing is there, I will take from 7 to 1. Okay. Tomorrow again we'll meet.